Hello, Advanced Math. I'm going to start on a topic related to ratios and rates today, but not exactly. A new kind of vocabulary word today. We're going to spend a few days on called proportional relationships. So we're going to start with number 1 today. You may be able to reuse some of the pages that you use today in future days. So go ahead and make this the title of your next page, and then close it up and give me all your new concentration. All right. So some things we've been talking about lately with ratios and rates. This is a problem we've done a whole lot of times. John walks half a mile each 1/4 of an hour. How many miles will he walk in 1 hour? Where I've always been asking you this question like in exactly one certain unit. What will happen? I could have just given you this situation without asking you for an answer. And we could have thought about this situation involving a ratio, where, we still know a ratio here of miles and hours. And I could have just not asked you for a certain one, and we could have just thought about the ratio this way. One way we did this back in the 6th grade part of the year is we made tables, if you remember, and we did things like saying, make a table of the hours, and we called that X, the one on the left, the X variable, and miles, Y. This was called a dependent variable, because the number of miles depends on the number of hours. So this was called an independent. A lot to remember there. And miles depends on hours, not the other way. You wouldn't say the number of hours depends on the number of miles. So when you look at that, we would say, okay, so we can make a whole lot of pairs of things we could do. If you walk in 1/4 of an hour, 1/2 of a mile. We also then would know in 2/4 of a mile, you went 2/4 of an hour, 1 mile. 3/4 of an hour, 1.5 miles. And then the one we've been doing was 1 whole mile, or 1 whole hour was 2 whole miles. And so I can make lots of pairs of things that he can do. And there's also 0 would be an option. In no hours he runs no miles or walks no miles. And so we made these data tables a lot back when we were doing the 6th grade part of this year. And we're going to revisit those a bit today. All right, so let's see. So I'm going to ask you we're going to worry about this new term called a proportional relationship today. And so here's my first situation. I've got this set of green tiles and this set of blue tiles. When there's 1 blue, there's 3 green. When there's 2 blue, there's 6 green. When there's 3 blue, there's 9 green. And I want to know, is there a proportional relationship between the number of blue tiles and the number of green tiles? And our strategy when we think about that today is going to be to use one of those data tables. So I'm going to first figure out here what seems to be dependent. Does it seem like the way they set this up, that the number of green tiles depends on the number of blue, or the number of blue depends on the green? Since this goes, it's kind of like 1, 2, 3. It seems like that's the one that we're starting from. So I'm going to just kind of say the blue is independent and the green is dependent. Because it seems to me how they set it up, the number of green depends on the number of blue. That's just what I would say. And so from this, I can tell that when there's 1 blue, there are 3 green. When there are 2 blue, there are 6 green. When there's 3 blue, 9 green. I could keep going. I could figure out what the next blue would be from the pattern given. And I could go back to 0 as well. If we followed the pattern down, 3, 2, 1, 0 blue would be 9, 6, 3, 0 green. So that's a data table for the number of blue and green tiles. And my question is this a proportional relationship? So let me show you what that means and how you would calculate it from a table. When you say, is this a proportional relationship, that means saying, are these all equivalent ratios? So I want to go ahead and make a proportion. If you remember what that is, that's most of your favorite ratio strategy. And so if I were to make all of these into ratios, this one's kind of hard to do, 0 to 0. But here, blue to green is, there's a ratio of 1 to 3. Here there's a ratio of 2 to 6. Here there's a ratio of 3 to 9. Here there's a ratio of 4 to 12. And are these all equivalent ratios is what I'm asking here. If you'll notice, this is times 2 times 2. This is times 3 times 3. This is times 4 times 4. And all these keep the same ratio every time. If I were to just divide them, you'll notice these are all equivalent to a third. Or if you prefer the decimal, all of these are, the 33 repeating decimal when I divide these. So these are all that or 1/3, 1/3, 1/3, 1/3. So in every ratio of blue and green that I can make, I get the same value here. This value, when I make the ratio of blue to green, has a fancy name. I'm going to type it instead of write it so you can read it. This 1/3 or 33 repeating that came up over and over and over again is called the constant of proportionality. And in this situation, it was always the same number, a third, a third, a third, a third. So when the constant of proportionality is the same for every point in the table, then you would say, yes, this is a proportional relationship. All right, let's look at another I do that is not, so you can see a counterexample. So this is the number of laps that Ryan swims in a certain number of minutes. 2 minutes, 2 laps, 4 minutes, 5 laps, 6 minutes, 7 laps. And you could continue this as well, right? Say looks like when you add 2 more minutes, plus 3, you add 3 more laps, and so on and so forth. And so what I want to know, is this a proportional relationship between the number of laps he swims and the number of minutes he spends swimming? So in order to figure that out, I have to find my constant of proportionality, see if there is one. So if I look at my ratios here, my first ratio is a 2 to 2 ratio, minutes to laps. My next one is a 4 to 5 ratio. My next one is a 6 to 7 ratio. My next one is an 8 to 10 ratio. And I want to know, are those, are those all the same, are those in proportion, are those all the same ratio, or are they not? And here it looks like they are not, because this has a ratio of 1 lap per minute. This has a ratio of less than 1. This is either going to be 8/10, or you could just say 4/5. So that less than 1 lap per minute. This is I don't remember that one off my head, that decimal. So you do a 6/7 is about an 85. It's a long repeating decimal, 857142. 857142. 85742 repeating, or 6/7. And then this is equivalent to that one, so that's 8/10 or 4/5. And here I do not have the same. These don't match. These are not all the same ratio. They're not equivalent ratios for the same value. So I would say no. This is not a proportional relationship because those don't match. The number of minutes and the number of laps are not always coming in the same ratio. All right, open your notebook. Let's do a couple together. All right, let's start with that one. So, another swimmer. Wayne swims 2 laps every 3 minutes. Is there a proportional relationship between the number of laps and the number of minutes? So for today, if you want to leave yourself space for future days, we're going to look at a table today. That's our first strategy or our first situation. And what I say here, the number of laps depends on the number of minutes, or the number of minutes depends on the number of laps. I would say the number of laps depends on the number of minutes. So I'm going to do minutes will be my independent, laps my dependent. That's not super important today. I'm just reminding you how it works. You would be fine if you reversed those today and did the laps on the left. It wouldn't matter. 2 laps every 3 minutes. So in 3 minutes, he swims 2 laps. 6 minutes, he swims 4 laps. 9 minutes, he swims 6 laps. And so on and so forth. And so what I want to do, move that a little, is I want to look into that constant of proportionality. Fancy word for is there a constant ratio no matter how many laps he's swimming here. So this has a ratio of 3 to 2, which is 1.5. This has a ratio of 6 to 4, which is equal to 3 to 2, which is equal to 1.5. And this has a ratio of 9 to 6, which is 3 to 2, which is 1.5. So no matter which data point I choose out of his number of laps, I always get this same constant of proportionality, the same, and really have the same ratio, just different versions, different multiples of the same ratio. And so I would say, yes, this is a proportional relationship, because all the ratios are equal. All right. And so that you have one in your notes, if you need to pause here and write this down, write the situation so that you remember it. And we'll look at some more strategies tomorrow here. And then unpause when you're done. Let's do one that is not going to be proportional so you can see that too. So this chart doesn't tell us what X and Y are. And that's going to be the case sometimes. So I wanted to kind of throw one of these in also. You can make up stuff. You can just say that this is like minutes and laps. Or this is, maybe you're buying something, like maybe this is like dollars and apples. I don't know. Whatever you want to do, you can make up values when they don't tell you what X and Y are. If it helps you think about the situation, you can do that. So when I look at my ratios here of X to Y, I want to know, I need that constant of proportionality to see. So my first pairing, my first dollars and apples or laps and hours or whatever you want to do, is a ratio of 3 to 8, which is, I know these decimals by heart. 3 divided by 8 is that, 375 thousandths. This is a ratio of 4 to 10. You know that decimal by heart. This is a decimal of 5 to 12. I do not know that by heart. 5 to 12 is 4, 1, 6 repeating. Only the 6 is repeating. And this is 6 to 14, which is 3 to 7, which is, doesn't really matter because I can already tell that this is not proportional. 4285 about. So these are not equivalent. All of these different ratios are not the same ratio. Whatever is going on here, I'm buying something, walking laps, or doing something, I'm not getting the same ratio all the way through the question. And so I would say this is not a proportional relationship. Whatever's going on with these two different variables, they're not related in proportion. Okay? So that's the first look at proportional relationships. We're going to look at some other ways to think about them in future days. But that's, I think, the first and maybe the easiest strategy to understand them. So if that was tough, go back and watch some examples again. Make sure you have great notes and places to expand on these examples for tomorrow, and I will see you then.